Hi everybody. Today we're looking at chapter 2, looking at computers, understanding the parts. Now, the first thing I want to say is how we define a computer. A computer needs to be capable of four things: input, output, processing, and storage. We need to be able to give the computer information. It needs to be able to give us back information. It needs to be able to take the information we give it and turn it into something else. And it needs to be able to store, remember. Oh, I'm a computer. Well, I'm not a mechanical one, but I can do all those things. I can accept data. I can process it in my mind. I can output the results of my thinking, and I can store in my, well, not as much as I used to be able to store in my memory, but yeah, I can store things in my memory. So yeah, I'm a computer, just not a very good one. Yeah, electronic computers are much better at all of those things than I am. With that said, computers are kind of stupid. When you get right down to it, the only thing that computers understand is electronical signal on or off. That's it. We represent that as binary signals 1 and 0, on or off. Okay? Either the current is going through the transistor or it isn't. Everything comes from that. Now, all those ones and zeros are not particularly meaningful to us as human beings. So we develop really elaborate coding systems that allow those combinations of zeros and ones to stand for symbols that mean something more to us. Here's an example of a coding system. So the character uppercase A would be represented as 01000001, or electric signal off, on, off, 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 on. Now, those 8 digits of that code are usually referred to as a byte. Each individual digit is a bit. As you can imagine, it takes a lot of bits and bytes to start representing anything particularly meaningful beyond an individual character. And also keep in mind that this is just one of a number of different coding systems that can be used to interpret zeros and ones in a way that human beings can understand, because this is just the Roman alphabet and the simpler Arabic numerals, and not a whole lot more than that. And we know that there are lots more alphabet systems out there, character sets, you name it. Takes a lot more bits and bytes to represent all those. But let's think in terms of this one. So 8 bits or a byte to represent a single character. So we can multiply these in massive quantities. So a kilo, which is the prefix that usually is intended to mean 1,000, the kilobyte is 1,024. Now, the reason it's not just 1,000 is because it's 2 to the 10th power. Well, and they're all divisible by 8 because computer programmers get very excited about things that are divisible by 8. So 1,024. If you remember that one, and then just remember that all the rest of them are not the exact prefix number, you'll be fine. So kilo, 1,000 bytes. Mega, million plus bytes. Giga, billion plus bytes. Tera, trillion plus bytes. And we go on to peta, exa, zeta, yada. Now, I still remember the first time I heard the term gigabyte, because, and this is going to date me, I know, my very first desktop computer that I had at the job I was working at had a 40 megabyte hard drive. Yeah, 40 megabytes. And that was a lot because we were in the information systems business. You know, that was our job. So we had the best of the best. Oh, God, I'm old. Anyway, the first time I heard the term gigabytes, my dad had gone to work doing consulting for Experian, you know, the credit reporting people, and they manage data in a lot of different areas. But anyway, he was talking about their gigabyte hard drives, and I'm like, Dad, you know, who needs gigabytes? And you know, now gigabytes are small. We need gazillions of them just to keep track of all of our photos and our movies and everything else. We need lots and lots of storage. But back then, most of our data was simple text and numbers, which didn't require a whole lot of storage space. And zetta and yottabytes are not that uncommon in large scale computers. And your average laptop probably has a terabyte hard drive at least. So, we're using lots and lots of those. But let's see what we get for those. So for 1 byte, we get that single character. Call it a single 1-inch cube with a letter on it. A tweet would need 208. Well, tweets are getting longer and longer these days, aren't they? This information is kind of old, I admit, but 280. So a shoebox full of blocks. A 3-minute MP3 song would take a whole shipping container full of those blocks. A small Instagram picture, a car full. A movie, 32.75 Olympic swimming pools full of blocks. Wikipedia, a layer of blocks covering Rhode Island 2.5 times. And Facebook's server capacity, and bear in mind this data is as of 2012. Told you it was an old piece of graphic here. 100 petabytes, or coating North America with blocks 2.8 times. Yeah, that's a lot of data. It really is. But, we're used to that now. The next thing we want to look at is the devices that manage these different functions, this input, output, processing, storage. So let's take a look at input devices. Okay? The most common input devices include things like keyboards, microphones. There's an example of an attached keyboard for a tablet. There's an example of a virtual, well, it's more virtual than a virtual keyboard. Usually a virtual keyboard would be one that's projected on a screen like on your smartphone or on your tablet if you don't have an attached keyboard. This one uses a Bluetooth device and projects a keyboard onto a desktop surface, and then it interprets your entries by the interruption of that signal. But really the most common ways that we interact with our devices these days are keyboard, whether virtual or physical, and microphone for voice interface. So, yeah, there are others, but these are the biggies. Okay? How about, a touchpad? Yeah. Well, useful for those virtual keyboards, but also useful for devices that are configured to accept touch input, which is really nice. Output devices. Well, what have we got for output? We've got monitors, we've got speakers, so visual output, auditory output. Ooh, 3D printers. That's physical output. I would love to have a 3D printer to play with. That would be so much fun. And of course, regular printers, whether laser printers, inkjet printers. Does anybody even own a dot matrix printer anymore? But yeah, lasers and inkjets are the most common. Inkjets being the cheapest, although in the long run more expensive to operate because you pay so much for the ink. Laser printers are a little bit more expensive to purchase, but the toner cartridges last for a long time. So I'm a big advocate of laser printers, except for the fact that if you want to do color, then that gets very, very expensive. So if you need color, go inkjet. Processing devices. Well, we know what we're talking about, the central processing unit for whatever device it is that you're using, whether it be a desktop, a laptop, a tablet, a smartphone. They all have a central processing unit that handles the manipulation of data and converting it into information. Okay? They may look a little different depending on the device, but that's the biggie, the thing. Yeah. Storage devices. We got lots of those to pick from. The classic hard drive, lots of moving parts there. We've got the USB thumb drive. Oh, there's RAM chips. These are storage. They're, high-speed memory, so you might consider it slightly separate from storage, but technically they are storage. Okay? All of these store information and make it accessible to our processor when it needs it. Some of them are more efficient than others. Then we have some devices that may be kind of hard to categorize, like the headset. The mic part is an input device, but the headphones, they're an output device because they're getting audio output. Okay? That touchpad, that's an input device, but it's also an output device because it's a monitor. Now, strictly speaking, in both of those, you have sort of separate parts of that overall device that are doing different functions. Here we have the microphone that is doing the inputs and the headphone part that is doing the output. In the case of the tablet, you have the screen that gives the output, and then there's an overlay that handles the touch input. But here's one we don't tend to think about too much. This is a graphics processing unit. It's actually a processor, but it's also an output device because it's manipulating graphics so that they can be output by our monitors more efficiently. So it's kind of a hybrid device. Yeah. The big question, of course, is how do we interact with our computers and devices? Now, engineers love to devise super complex interactivity because that's what they're good at. They're good at complex devices. But we as users like things that are really, really simple. Eh? So an engineer would love this, the cockpit of an airplane. Look at all those switches and dials and you name it. Very complex. But if you're a pilot, you understand what all those things are for and you understand how to use them. But does anybody remember when the first one of these came out? Ah, we were just entranced by the simplicity. It was just a little screen and a touch wheel. That was it. And yet it did so much. Now I know these have been absorbed into our smartphones now, so very few people even have an iPod anymore. But when it came out, we were just astonished by the simplicity of it. Now, of course, we like to communicate with our devices simply by talking to them, if we possibly can. We like to be able to, hey Siri or hey Alexa or whatever it is. And that brings up two important topics: voice recognition and natural language processing. And these are two very separate things. Okay? Voice recognition is whether or not the device can understand the words that we say. Okay? That's it. Can it understand the words that we say? And if you've ever tried to dictate a text message while you're driving in your car, you know that that can be very frustrating. They're way better than they used to be. I remember the first computer I had that did voice recognition, and I had to read to it for hours before it got used to the sound of my voice and how I pronounced things. And let's face it, everybody talks differently. So voice recognition is an incredibly complex task for computers to handle. Natural language processing is another thing altogether. This is the computer not just understanding the words that we say, but the meaning behind them and how we use them to instruct the computer in what we want it to do. And that is incredibly complex. Very, very difficult for computers to do. But there's a computer that was designed simply to manage both of these tasks. It's called Watson, and it was built by IBM. It was built with the purpose of understanding speech and understanding natural language processing, being able to take instructions via spoken word. Actually, it was built for a very specific purpose, and that is to play Jeopardy!
I remember that morning going to the lab, and I was thinking, this is it. This is the last Jeopardy game.
This is Jeopardy! The IBM Challenge.
Here we go. Brad, if you're ready, make your first choice.
Let's take alternate meanings for 200, Alex.
4-letter word for a vantage point or a belief. Brad.
What is a view?
Yes.
After the first clue of the game, which Brad won, I had just this horrible feeling at that moment that he was as good as everyone said he was, and he was just gonna run the whole board on us.
Watson.
What is shoe?
You are right.
We actually took the lead. We were ahead of them, but then we started getting some questions wrong.
Watson.
What is leg?
No, I'm sorry, I can't accept that.
What is 1920s?
No.
What is chic?
No, sorry. Brad.
What is class?
Class, you got it. Watson.
What is Sauron?
Sauron is right, and that puts you into a tie for the lead with Brad.
The Double Jeopardy round of the first game, I thought was phenomenal.
Watson went on a tear.
Watson.
Who is Franz Liszt?
You are right.
What is violin?
Good.
Who is the church lady?
Yes. Watson.
What is narcolepsy?
You are right, and with that, you move to $36,681.
The risk was, if Ken gets a daily double, bets big, gets it right, he's gonna be well ahead, and then with that kind of lead going into Final Jeopardy, if he bets enough, he could end up winning the match.
Ken.
What's a committee?
We got to find that last daily double. We got to find that last daily double.
It was a crucial moment in the game. There was still a daily double on the board, and it was starting to become pretty clear that it was in the legal ease category. Let's go to legal ease for 1,200.
Watson.
What is executor?
Right.
Same category, 1,600.
Answer, daily double.
That was the moment when I knew it's over.
The category is 19th century novelists.
What Watson wants to do then is preserve the lead, not take a big risk, especially with Final Jeopardy, because just like for humans, Final Jeopardy is hard for Watson.
Now we come to Watson, who is Bram Stoker, and the wager. Hello, 17,973, and a two-day total of 77,147.
I would have thought that technology like this was years away, but it's here now. I have the bruised ego to prove it.
My past Jeopardy experiences have been great, but they weren't really weighty with this kind of technological, philosophical importance. I think we saw something important today.
Didn't really think very much about the implications until later and say, wow, wait a second, this is history.
Of course, this whole project is not ultimately about playing Jeopardy. It's about doing research and deep analytics and a natural language understanding. This is about taking the technology and applying it to solve problems people really care about. We're just so excited about all the things we can do with this.
I had thought this is the end. We get there, we're done. And I'm realizing it's just the beginning.
I actually tuned in to Jeopardy the night that that episode was aired, just serendipitously, because my son really liked watching Jeopardy at the time. And I was just blown away to see that. And Nova actually did an episode about the whole design process of Watson, which is wonderful. And you can see a version of it on YouTube if you're interested in pursuing that further. And I think we'll be looking at Watson again in this course. But it's an amazing accomplishment in language processing and just computer understanding, because they had to let the computer loose on its own to learn things by feeding it thousands upon thousands of Jeopardy questions so that it could learn how they worked. Because, well, maybe, watch the video and you'll find out a little bit more about it. I confess, my brother was involved in a project, a combined project with IBM, and actually got to meet Dave Ferrucci, the lead guy on the Watson project. And I was so jealous because I was, kind of fangirling a little bit. But this idea of just being able to talk to a computer and have it understand you and, do the things that you want it to do, that's where all the research is now. Now, if you're interested, Watson, after winning at Jeopardy, went on to do many other things and is still out there working in research. He's working in medical diagnostics. For a while there, you could have your taxes done by Watson technology. And there's a few other things that you can check out. But yeah, so that's it for chapter 2. I will see you in the next chapter. Good market,